this video, we will see a problem on calculation of stresses on all four corners. Here is the question. Calculate the normal stresses at four outside corners of horizontal short section of hollow pier ABCD. So here we have a hollow column ABCD. I'll write that in the form of data. The first thing is we have a hollow column which is ABCD, and the question is to find the normal stresses at four outside corners. That is, we have to calculate the stress at corner A, next stress at corner B, similarly at C and at D. Now these four stresses we have to calculate. It is given that a hollow pier is ABCD, 2.5 meters square outside and 1.5 meters square inside. So the dimensions of the square are given. Supporting a load of 140 kilonewton, P is 140, we'll denote the load by P. So 140 into 10 raised to 3 Newton. And the load is on diagonal AC at a distance of 0.6 meter from diagonal BD. So 0.6 is the eccentricity. Now with the data given, let us try to get the solution to this problem. The first thing in this question is we have to draw the diagram. Here it is given that we have a square on the outside, there is square even inside. So it is a hollow square section. So here is the hollow section, and I'll mark the corners here. We have corner A, corner B, this is C and D. The dimensions of the square are given. It is written that 2.5 meters square outside. So it is 2.5 meter outside and 1.5 meter square inside. So the inside square, it has a dimension of 1.5 meter. Similarly, here I have marked the width. Even the depth would be same because of being a square section. So this is a square section, and here in this problem it is given that the eccentricity is on the diagonal, so we have to join the diagonals here. Here we have diagonal AC. Next we have diagonal BD. Now joining the diagonals, it is said that supporting a load of 140 kilonewton, which is on diagonal AC, and it is at a distance of 0.6 meter from diagonal BD. So from diagonal BD, 0.6 meter distance, here the load is located. This distance is eccentricity E. Now, here we have to calculate the stresses at all the sections. So once we have drawn the diagram, now the problem becomes really simple. The first thing is we should get the area for this hollow square section. So I'll say that since cross section area for hollow square is given by capital A is equal to outside square 2.5 into 2.5 minus inside square 1.5 into 1.5, that gives me the answer as 4 meters square. After getting the answer of cross section area, now if we look into the problem, here the load is eccentric at value E. So because of the eccentric load, there are two kinds of stresses, direct as well as bending. So I'll write down because of eccentric load, direct as well as bending stresses are induced in the section. So as the load is eccentric, otherwise if the load would have been axial, that is passing through the axis, then it would have been only direct stress, which is compressive, no need of bending. But here, since it is eccentric, there is direct as well as bending stress. So let us go for the calculation of direct stress first. Since direct stress is given by sigma suffix d is equal to P upon A, that is load upon area. So therefore, the load in the problem, it is given as 140 into 10 raised to 3 Newton. Area is 4. So therefore, direct stress value, this comes out to be 35 into 10 raised to 3 Newton per mm square. And here the unit, it is in terms of meters. So stress will be Newton per meter square. After getting direct stress, I'll say that therefore bending stress is given by sigma b is equal to m by z, keeping this as equation number 1. So now bending stress is m by z. So I'll go for the calculation of m first. That is, I'll write down, since bending moment is given by m is equal to P into E, load into eccentricity. Therefore, here I will be getting the answer of bending moment as, by putting the values, load is 140 into 10 raised to 3, eccentricity is given as 0.6. So therefore m value comes out to be 84 into 10 raised to 3 Newton meter. Now after getting the value of bending moment, the next thing is to calculate Z. Z is called as section modulus. So since section modulus is given by Z is equal to I upon Y, keeping this as the second equation. Now here After that, I'll calculate the length of the diagonals because it would be required. So starting with BD, here as we see in triangle BCD, I'll separate it. In triangle BCD, BC is 2.5 meter and even CD is 2.5 meter. So we can get the value of BD by Pythagoras theorem. So in triangle BCD, BD is equal to root of BC square plus CD square. BD is root of 2.5, which is BC, plus CD is 2.5 square. So the answer of BD, it comes out to be 3.54 meter. After getting BD, I can say that even AC is of the same dimension because it is a square. So AC is equal to BD and that is equal to 3.54 meter. Now, as I have used this triangle, similarly, the inside points of the square, I'll name them as E, F, G and H. So here I'll also calculate this inside diagonal, which is EG. So for that I'll draw the diagram. In this triangle EHG, EH is 1.5, HG is 1.5. So I can easily get the value of EG. So again I'll say that similarly in triangle EHG, by Pythagoras theorem, EG is equal to root of EH square plus HG square. So therefore EG is equal to square root of 1.5 square plus 1.5 square, and therefore EG, it comes out to be, it is 2.12 meter. Similarly, the other diagonal inside, which is FH, will be also same. So FH is equal to also 2.12 meter. The next thing is, after getting this, we can get half of the values, that is from the center. I'll call this point as M, that is the midpoint here. So once I know AC, I can calculate AM as well. Next I'll say that therefore AM is equal to half of AC. So here we have half of AC, it was 3.54, same as BD. So therefore I am getting distance AM, it is 1.77 meter. Similarly, the distance capital E up till M, that will be half of EG. So half of 2.12. So therefore EM value, it comes out to be 1.06 meter. Now after getting all these values, why we have calculated them, it would be used in the calculation of moment of inertia, because here as we see the eccentricity is given with respect to diagonal BD. So we need to have moment of inertia about diagonal BD. So here I'll say that since MI about diagonal BD, that is moment of inertia about diagonal BD, is given by, it is IBD, and here there is an interesting thing, that if we want to calculate the mi about BD, it is nothing but the mi of outer triangle, which is ABD, minus mi of inner triangle EFH about its base. And like this we have two triangles. So here IBD is nothing but 2 into mi of triangles about base. So for this I'll explain it here, that I am taking only the half triangle. Here we have the outer triangle as ABD, inner triangle as EFH. Now, as it is clear that I will be calculating the moment of inertia for this first triangle and then multiplying it by 2, I'll get it for the other. So how the formula would be, IBD will be equal to, I am writing 2 here because we have another triangle which is at the half of the section, which is at BCD, another triangle. So we have to find out the mi about BD for only this red section. There is no material in here. So 2 into, the formula will be BH cube, I'll write down capital BH cube by 12, that is the capital B and H value for the outer triangle. Next, minus small BH cube by 12, that is for the inner triangle. I'll write down, since mi about base for a triangle is equal to BH cube by 12, I have used this formula. So now here I'll put the values. Therefore IBD is equal to twice of capital B. Now what is capital B? It is the length of diagonal BD, because this is the base of the triangle we are considering. So capital B is nothing but BD, and the value we have calculated, BD was 3.54. Next, capital H. Capital H is the height from of the outer triangle, and this is A up till M. This is capital H, and the value was, it came out to be 1.77. So here I have 1.77 cube divided by 12. So now capital B, that was 3.54, and capital H, it is 1.77, that is nothing but AM. This was capital H. Now we have small b and small h. Small b is this base, which is HF. This is small b, and small h is the height of this inner triangle. So here I'll put the values, minus small b, we have found out it was nothing but FH, and FH value was 2.12. Then height, we have found out it was the height of the inner triangle, that came out to be EM, and EM was 1.06. So it is 1.06 cube divided by 12. So from this we get the value of I suffix BD, that is the moment of inertia about the diagonal, and my answer is 2.0 833 meter raised to 4. Now after getting IBD, here we need to know what is the distance of this axis BD with respect to either point C or point A, that is same, so it will be exactly at half of AC, we can say. So therefore distance Y is equal to half of AC, and it is 1.77 meter. After getting I and Y values, the next thing is, here we had written in equation number 1 m upon z, so I'll say that therefore from equation 1 sigma b bending stress is m upon z, and z is nothing but I upon y, so y goes into the numerator. Here I'll write down, since section modulus is I upon y, so therefore I'll put the individual values. Bending moment, it was 84 into 10 raised to 3. Y value we have found out, it is 1.77, and mi is 2.833. so from this I'll get the value of bending stress, and my answer comes out to be, it is 52.39 into 10 raised to 3 Newton per meter square. Now here we have found out bending stress. Previously we had direct stress. The question is to calculate the stresses at all four corners. Now we will start with this. So the first thing is stress at corner A, that will be equal to, at corner A we can say that here the load is closer to corner A, so there will be direct as well as bending stress at A, so that is sigma D plus sigma B. Sigma D, it was 35 into 10 raised to 3, sigma B 52.39 into 10 raised to 3. So therefore stress at A, that comes out to be sigma A, I will denote it by, it is 87.39 into 10 raised to 3 Newton per meter square. And here this is the only chapter in which we take compressive stress as positive, so this answer is positive, it means it is compressive stress. Now after getting stress at A, the next thing is to calculate stress at B. See, direct stress will be there on all the corners, so stress at B, that is sigma B, is equal to direct stress, and here as we see the eccentricity is located at 0.6 meter distance. I'll explain it really quickly, that since the eccentricity, here I will draw the diagram in this way, eccentricity is 0.6 meter, so the distance is, this angle is 45 degree, which is the angle here, and if I find out both the values, both of them come out to be 0.42 meter. So here the eccentricity are same with respect to x and y axis, that is with respect to x the eccentricity is same 0.42, and even with respect to y it is same 0.42. So when ex and ey values are same, then load which is there on that diagonal, only on that diagonal the stresses would be there, that is the effect of bending would be available only at A and C, not on B and D. So B will be subjected to only direct stress because eccentricity is same and the load is not there on diagonal BD. So here the effect is only direct stress. So stress on B, that comes out to be 35 into 10 raised to 3 Newton per meter square. Again, as this answer is positive, it is compressive stress. Next, stress at C, that is sigma C is equal to, now we see here, opposite to A there is C. On A we were having maximum stress, on C there will be minimum stress. So here it will be sigma D minus sigma B, because the load is far away from point C, and that is 35 into 10 raised to 3 minus sigma B, which was 52.39 into 10 raised to 3. So therefore sigma C, it is minus 17.39 into 10 raised to 3 Newton per meter square. And as the answer is negative, the stress is of tensile nature, because this is the only chapter in which we take compressive stress as positive, tensile is taken as negative. Then stress at D, that is sigma D, is equal to, again as I have told, that on point B and D there will not be bending effect of P, there will only be direct stress. So on D also there will be direct stress, so it was sigma D and 35 into 10 raised to 3 Newton per meter square. This answer is positive, so compressive. So here in this video we have seen the question in which they were telling us to calculate the values of stresses at each of the corners on the outside, that is stress at A, B, C and D, and we have found out all the values starting with A and reaching up till point D. And it is clear that at A we are getting the value of stress which is maximum, sigma max, and at C we are getting the value which is minimum, so this is sigma C. Looking into the diagram, load was close to A, so maximum stress, load is far away from C, so minimum stress, and with this we complete the problem.